Greetings. We're going to do a little video on the discussion question about average body temperature. Okay, a couple things about hypothesis testing before we get started here real quick. Is that hypothesis testing is a fundamental to any elementary stats course, and it's something that we really want to understand. But typically in a course, in a statistics course, you are given summary statistics. You are given the mean, the standard deviation, the sample size, or something of that nature. Well, that's not how it's done actually out there in the real world. In the real world, you won't be given the summary statistics, you'll be given the raw data. And so when we go to conduct a hypothesis test with raw data, that's where in our studio have their strong suit, because it's a real world tool. It's used or designed to be used in the real world. So we're going to go ahead and run this test, and it's going to have summary statistics, and we're going to have to do some of the calculations by hand. But when we have raw data, those calculations will be done by R. R will do them for us. Now, there's a really good example in the lab, I believe it's lab 7, about how to actually go in and run a hypothesis test with raw data. It's the one on miles per gallon. So review that one if you want to see how you go about and do a hypothesis test with raw data. This one is going to be how do we do a hypothesis test for a single mean using summary statistics. Okay, with no further ado, let's go ahead and get into it here, okay? So in this particular one, let's get to the right slide here. There we go. A study was conducted to test the hypothesis that the average body temperature of a human is 98.6 degrees Fahrenheit. We're assuming a healthy human. The researcher believes that the average body temperature differs from what was stated, the value of 98.6. Okay, so they want us to state the null and the alternate hypotheses symbolically. And they want us to do, in other words, they don't want us to say the average body temperature is 98.6 or the average body temperature is not 98.6. In other words, they don't want the null and the alternate written in English. They want it written in geek. They want it symbolically. So let's go ahead and do that. Let me get my pen out here. And so that says that the null hypotheses would be that the mean is as stated. It's 98.6 degrees Fahrenheit. Now remember that the alternate hypothesis, H sub A, is always going to be the researcher's hypothesis. And our researcher here thinks that the body temperature differs from 98.6, right? Notice the word differs right here. That's important because that tells us that means that mu is not equal to 98.6. If he had said it was greater than 98.6, we used a greater than, or a less than 98.6, we would have used a less than. Okay. Now, they didn't ask us to do this in the problem, but let's take a moment, so once we've set up our null and our alternate hypotheses, and talk about the assumptions of the test. We're looking at a test of a single mean here, which means that the test that we're going to run is a t-test. And a t-test has some assumptions that go with it. And again, one more time, why did I know that I'm running a t-test? Because I'm running a test about mu here, about a single mean, okay? And since I have a single mean that I'm testing, I'm going to use a t-test. As it turns out, as we'll see in later work, if we have two means, we'll use a t-test also. But if we have more than two means, we're going to use this really cool thing called ANOVA. All right, anyway, let's get back to the test at hand here. So a couple of assumptions that we need to check. We need to check independence, and we need to check normality. All right, so in the case of independence, we can assume that we're going to have to assume that our researchers did a good job. So in other words, they did a good job of getting a random sample, and since they did a random sample, we can assume independence between each of the samples, and we can also assume that we sampled less than 10% of the population. As we'll see in the coming up here, they sampled 35 people, which is going to be much less than the 6 billion Homo sapiens that are living on the planet right now. Okay, the second assumption that we have to assume is normality, and as we'll see in the next slide here, is that the sample size was n was equal to 35. So since we have a sample size of 35, the central limit theorem is going to kick in, and we know that the distribution of x bar is going to be approximately normal. So since the distribution of x bar is going to be approximately normal, the normality condition for the parent distribution is less important. In other words, if we know that we've got a large sample size, not really necessary that we have a normal distribution that we're sampling from for these results to work. Okay. All right, cool. So that's pretty much what we got going in part A. Part B, our researcher gets out their trusty rectal thermometer, oh well, maybe not a rectal thermometer, and gathers up body temperature from 35 healthy subjects and calculates the sample mean to be equal to 98.2 with a sample standard deviation of 0.98 degrees Fahrenheit. So they came up with an X bar equal to 98.2 degrees Fahrenheit, and they came up with a sample standard deviation S equal to 0.98 degrees Fahrenheit. Okay, and they said that their sample size here, n, was equal to 35. So this is what I was talking about in the opening when we start here, that they did not give us the raw data. We didn't have the numbers to crunch and calculate X bar and S. They did that for us. And so now they're expecting us to calculate the t-test statistic based upon the sample. Well, the t-test statistic is equal to X bar minus the mean of the null hypotheses divided by the standard error of the distribution, which is given by S over the square root of n. And there was a fair amount of confusion among folks about how do I go about getting that number. In other words, where does that number come from? So let me back up here to the previous slide. Whoops, went right past it, my bad. And note that this value right here, this guy right here, in fact, let's go back into the same colors, go red here. This this number right here is the means of the null distribution. In other words, whatever the null distribution says mu is equal to, that's mu sub 0. So when we come back over here and do our calculation, we got the right spot here, that's going to be the 98.6. Okay, so let's go ahead and plug everybody into T here. So it's going to be 98.2 minus 98.6 divided by S, which is 0.98 over the square root of 35. And that's going to be my t-test statistic. Now, of course, you could calculate that using your handy-dandy Texas Instrument calculator, or pretty much any calculator, but I think I'm going to go ahead and do it all in one swell foop in RStudio. Now, since I'm not being expected to turn a script here, I'm going to use the console, because remember, the console is just like working in a calculator. So I'm going to do all of my calculations right here. So I'm going to go ahead and name that as t-obs for t observed, and that's going to be equal to 98.2, which was what the sample value was. That's my X bar. Okay, remember, we got to put that in there. The first number is X bar, which is, 98.2. Subtract from that 98.6, and then we're going to divide that by, and I'm going to set a parentheses for the denominator here, the standard deviation, which is 0.98, divided by SQRT for square root of 35. Okay, so if I hit an enter, now that number is in TOBS. Let's go take a look and see what TOBS is. And so I get it to echo for me, and we notice that our t observed is negative 2.414726, which is a really long ways away from 0 when we're thinking about a normal distribution. So let's go back over to our whiteboard here, and let's go ahead and write that down. So we came up with our t observed was negative 2. I got the memory of a flea here. What was it again? It was 2.414726. If I don't talk for a minute, it'll stay in my head. Okay, sorry about that. Okay, so what do we know about that? Okay, so what do we know? Well, we know that that is a long ways away from 0 in a t-distribution. So remember, a t-distribution and a z-distribution, a standard normal distribution, are kind of kissing cousins to each other. It's just here that the shape of this t-distribution is based upon the degrees of freedom. And we know that degrees of freedom are equal to n minus 1, to whatever the sample size less 1 is. So we know that our degrees of freedom here are equal to 34. So that t-distribution is centered at about 0. The observed t-test statistic was negative 2.414726 standard deviations below the mean. In other words, it's way down here, okay? Remember, our interpretation of t and z are really identical to each other. It's telling you the number of standard deviations your observed value fell away from the hypothesized mean. And that's a lot of standard deviations. So we're going to do the p-value in another picture or another page, and I'm going to redraw this whole drawing when we do it, but realize that that shaded region right there, along with this shaded region right here, are going to constitute the p-value. In other words, those two areas combined make up our p-value. So this is a two-tailed test. Why do I know it's a two-tailed test? Well, let me go back for a second, and we see that our alternate hypotheses right here contain the condition of not equals. So when we have a not equals, that tells me that it's a two-tailed test. There's some good examples of this in the questions form, if you go take a look in the question form in Canvas, okay? All right, so let's see, where were we? All right, so we finished up that part. We now know what our t-test statistic is. Let's go take a look, see A, B, C. There we go, part C here. It says make a decision as to which hypothesis support. Oh, wait a minute. Did I skip a part here? Let me come back here. Sorry about that, guys. Let's see, A, B, the test statistic, and oh, to make, I'm sorry, I just misread it. Let me read it again here. It says to make a decision, we need to know what the p-value is. So it says calculate the p-value to 5 decimal points. Okay, so we're going to go back and redraw the drawing that we just did and use that to help us figure out what we're going to do in R, okay, in our studio. Again, this is a t-distribution with degrees of freedom equal to 34, and our test statistic was negative 2.414726, okay? So this shaded region down here corresponds to half of our p-value. So if we find that value right there and double it, that'll give us the entire p-value, because as it turns out, since we're centered about 0 and we're symmetric, these two tails combined are going to give that to us. So how do I go about doing that? Well, we're in luck because we know that PT sums from the left. So we're going to put in PT and we're going to put in TOBS, or the T observed value, and then we're going to put in the degrees of freedom. And those are the only things you need to put in to PT in order to get the values back, okay? So since we stored our test statistic into TOBS, we can do that directly, or you can actually just type the number in. You can say PT negative 2.414726 by 34, and you will get your corresponding p-value. Well, not quite. It's going to give us half of it. I apologize. It'll give us half of it. So what we're going to have to do to get the p-value is we're going to have to multiply this by 2. And that, my friends, will be our corresponding p-value. All right. So let's go back over to our studio and let's go ahead and do that. So I'm going to say my p-value is equal to 2 times PT, and then I'm going to put TOBS in there for T observed, comma 34. Okay, and I hit an enter, and it says object P not found. Okay, I paused for a minute to figure out what I did wrong, and I didn't want to say p-value. That's just making my life hard, so don't do that, okay? Because it assumed I wanted to do a subtraction there. Okay, anyway, so 2 times pt, and then we'll put in our t observed, and then put in our degrees of freedom, which is 34, and we get the following p-value, which is 0.021 blah, 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 blah. So I'm going to come over here and make my life easy. And what I'm going to do is I'm going to copy that number because I'm going to need to paste it back in to the actual question here. Okay, so let's go back over to Paintbrush. And they said they want it to 5 decimal places. So calculating that to 5 decimal places, that's equal to that number right there. Okay. All right. So now, once I've done all these calculations, what does it mean? Okay. Well, someplace along the line, we were supposed to state a decision rule. So we didn't do that yet, which is kind of bad form. But let's assume that we had. And more than likely, what we would have done for our decision rule is we would have said, reject the null hypotheses if the p-value is less than alpha. In this case, less than 5%. Almost always, unless you're told any different, you're going to set your alpha to 5%. Okay, so this right here, this number is our p-value. And our alpha, which would be what 5% is 0.05 or 0.05. That would be our alpha. And so what we see is that our p-value is 2%, which is less than alpha. So our decision here is going to be to reject the null hypotheses. And that's a fundamental that you need to really make sure you got, okay? Put a sticky note on your mirror, take a look at it every morning about the different ways you either fail to reject or reject the null hypotheses. So if the p-value is less than alpha, we reject the null hypotheses, actually less than or equal to. If the p-value is greater than alpha, then we fail to reject. Okay, one last question on this thing, and I'm just going to talk it through you a little bit and let you write up your own paragraph. It says, based on your test statistic T in part B and the p-value in C, which hypothesis is supported? Okay, well, supporting a hypothesis tells you which one did you not reject. So we're going to support HA. Then we're going to support the alternate hypotheses that in fact the mean body temperature is different than 98.6. And now they say they want you to give the response in context of the problem. This means your response should be roughly a paragraph in length. So what do the results mean? Well, the null hypothesis says that mu is not equal to 98.6. X bar was equal to 98.2 degrees. So it appears, based upon our intrepid researchers' work here, that the mean body temperature is actually less than 98.6 degrees, the hypothesized value of the null hypothesis. And in fact, the alternate gets our support in saying that we are hypothesizing that it is different than 98.6, but we could go a bit further in saying, based upon our number, it appears that the average body temperature is less than 98.6. It's somewhat smaller than that. And we can construct a 95% confidence interval if we care to give bounds upon that particular statement. But that wasn't asked here, but if you feel like doing it, you can. All right, please give me feedback if this helped at all. Let me know if it helps you get further along the road. And keep posting questions and I'll be happy to answer them.